Good morning. This is E637, and oops, my hair needs to be adjusted. And I'm Charles Bouman. This is Digital Image Processing 1, and we have an entirely new look this year because, first of all, we got a 16 by 9 screen, which is really appropriate for image processing since now we're in the high-def format, although I've been told it isn't fully high-definition resolution, but we can pretend. And also, I kind of like the figure in the beginning, the black and white motif. It was kind of seemed a little bit more stylish to me. So those are all good signs for the future. It looks like we have a packed class this semester. Oh my goodness, every single seat. Oh, there's one empty seat there. Are you okay? Right. Yeah, okay. And we have like some off-campus students too. I think last time I checked there were 9. So, and there's our occupant of our last seat. So now we got, or perhaps, maybe, no. Yes. Okay. Anyway, so let me see. So today's class, mainly what I'm going to be doing is just talking about what we cover in the class and how the course is organized and those sorts of things. And, feel free to ask questions. I know that sometimes we used to call this TV, but it really isn't TV anymore. But this sort of online video format maybe makes people a little bit more cautious about asking questions, but you shouldn't be if you have any questions. Okay, so let me go to the presentation. I have my presentation material on 8.5 by 11 sheets. So maybe what I'm going to have to do is reformat things because now that we have the high def format. But anyway, first of all, the title of the course is Digital Image Processing. Digital Image Processing 1. So a lot of people ask, well, what background do you need for this class? And this has no graduate course prerequisites, but it does. I always tell people that, well, the official prerequisites are 301 or 302. Obviously, a lot of people won't have taken those because those are undergraduate courses at Purdue or equivalent. But what I really tell people are the prerequisites for this course is that there's 3 things you should know before you take this course. You should know some linear system. Well, okay, there's 3 things you should know, but you only really need to know 2 of them. So if you don't know one of these, don't panic, okay? So you should know some linear systems background, so the Fourier transform, linear time invariant systems. If you have a computer science background or a biology background, you may not know too much about those, but don't panic. That's more material that covers more intensely at the beginning of the course. You should have some probability background because we'll use probability in this class. So that means some undergraduate courses in probability. If you've taken 600, that's terrific. Or 302 would be the undergraduate probability course. And then the third thing you need to do is have some experience with programming computers. So we have a fairly extensive set of labs, and we'll use MATLAB and C. So I don't know, maybe there'll be some future day in which I will stop requiring this, but I think even today it's very important to be able to program in a high level, what used to be called, a basic, I don't even know what the term, they used to be called high level languages, but now they're much higher level languages, so I don't know what the correct terminology, but like C or I guess an equivalent C++ or Java, but I don't know Java. And C is so all our projects will be in C. If you want to use C++, that's okay. But I want you to be able to write programs in C because it's still the case that programming languages are widely used for real implementation of systems. They're much more efficient. And you need a little bit of experience. Even if you're good, I've had people who were very good C programmers, and they come in, when they have to program in image processing applications, I think they're shocked sometimes that they're not as adept at it as they thought that they might be, because the techniques are somewhat different. So particularly a lot of things having to do with dynamic memory allocation and so forth. So the three things you need to have are linear systems, probability, and some programming experience. So if you have two of those, you're great. If you only have one of those three, it'll be more challenging. We often have students that take this class from civil engineering, because I know there's a lot of people in civil engineering who do imaging, or sometimes biology or biomedical, and those people often don't have quite as much background, but I think that the course is designed that people can still do well in the class, even without. But if you're concerned, you can come and talk to me. We're going to need a teaching assistant because the class is big, but I haven't been assigned one by the department, so I'm working on trying to recruit somebody as a teaching assistant. I have a person I think will probably be doing it, but I'll need to work on that and see. So that's left blank. There's a book, an official textbook for the course, but you don't need it. So it's very. I have it listed there mostly as it's literally a handbook, and it has useful information for people who do imaging research or work in the imaging field. So I think there's a newer edition than that. So, but don't buy it just for this course, because you won't really need it for this course. It's more of a broader handbook. So I know that some of you are on a budget, and I don't want you to spend your money on something that if you don't have it. And then there's a set of books I listed here that are good, like background references. If you haven't had linear systems theory, the undergraduate class we teach here on linear time-varied systems is 301. Actually, I teach that sometimes, so I have notes on my website. And the textbook we use is by Oppenheim and Wilsky. So if you get a copy of that book, I think it's a very good book. You can read it yourself and learn the material. If you need any help with that, come and talk to me. I have some image processing books here, and then a C language textbook. Okay, so the course has three objectives, three major objectives in my view. The first objective is to cover the basic analytical methods of image processing. So this is sort of the theory of image processing. The second is to cover some of the technology of image processing. So you've become familiar with what the sort of challenges are and what the current physical systems that people use are, and how the actual art, you might say, of image processing is practiced. And then the third bullet, which is sort of primarily an objective of the laboratories, is to learn how to actually implement real algorithms and systems in software. That's typically how image processing systems are implemented in the software on either general purpose processors or DSPs. Sometimes they're implemented in VLSI, but VLSI systems, also have software design tools. So software is sort of a key component, and you'll get experience with that in the labs. And as I said, we're going to do them in both MATLAB and C, so that you're forced to learn it. I've actually had people who are good C programmers say that they had a lot of trouble learning MATLAB. But most people know MATLAB and then have to learn C. But if you can have no background in C, and by the time that the course is done, if you've successfully completed it, you'll have learned C, okay? It may not have been a totally pleasant experience, but you will have learned it, okay? And basically, it's not as horrible as it sounds, because it's like on-the-job training. I give you like templates of basic programs, and you modify them. So you kind of learn it as you go. And it's not so bad, I think. So then, so let's see. The grading policy is there are two midterm exams and a final exam, and then the computer laboratories are worth 15%. I'm going to talk about this extensively in a few minutes because we have to talk about academic honesty policies. So I should warn you that, okay, so the labs don't count like a huge amount. 15% is not, so the amount of time that the labs take you is disproportionate compared to the percentage of the grade. Now, there's a number of reasons for that. One is that I just think it's more, well, there's a lot of reasons why I don't count the labs more heavily. But I think that the value of the labs is also you learn the basic material so that you can do better on the exams. But I should warn you that the exams are somewhat more theoretical in their content than the overall balance of the course lecture and lab material. I try to put some practical problems on the exams, but the exams tend to be a little more theoretical in nature. So you shouldn't get caught off guard with that. When you study, I'll talk about how you prepare for the exams in a few minutes, but basically I post all the old exams. So you can go back and work out all the old exams, and I have, I prepared like essentially like a syllabus, you might say. It's really, I have a syllabus for the course, which we'll go over, but I prepared a work plan, you might say, for how you can look at the different old problems. So I organized them by topic, because what happens is that, well, like for instance, the final exam is cumulative, so it contains problems from topics throughout the semester. So I organized the different problems in the different exams by topic, and you can go back then and you can study them as we move through the material. But I'm not going to collect, so you can think of those as homeworks, essentially. The homeworks for this class are essentially the old exam problems. Most of the old exams, I think, have solutions with them, but my suggestion is you try to do the problems without looking at the solutions. So if you can do all the problems from all the old exams, assuming that I don't represent a step discontinuity, like nothing discontinuous happens to me, which I hope I don't want anything discontinuous happening to me. So that then my next exam should be statistically, pretty much similar to the previous. I should be a stationary random process, okay? So my exams should pretty much be similar. So you should be able, if you can do all the old exams, you should be able to do the new exams, right? So there's no mysteries there. Okay. And then I just add the grades up and I rank them and apply grades. I put thresholds, obviously. I should say something about what the average GPA. You can probably look up what the average GPA is for this course. Gee, I'm afraid to even say because I don't even remember. But I pretty much, you can look back at old semesters, and the average GPA for this course is fairly invariant, unless I sense that, for some reason it was a particularly strong or a particularly weak class, and I don't anticipate that would happen. But I guess I should say is that, to get a D in this class, you have to really earn it. Okay, you have to work hard and be diligent in your efforts. Okay, okay. To get a C in this class, you have to, not do a good job by any reasonable standard, in my opinion. Okay, and that means that you have to not do all the labs. So it's very important to do all the labs in this class. There's no excuse for not doing all the labs in this class. And you have to do very poorly on the exams. So most people get B's and A's. Okay. The labs. So my hope is that when you do the labs, everybody should get the right answer, because if you don't know how to do a problem, you can come and ask me. Or if and when we get a TA, which I'm hoping I'm going to get, presuming that I can find a person that I can hire. I have, and hopefully it's a person who's, got a lot of experience with this course. And I always tell them to let you know how to do the problems. So in other words, everybody should get 100 on the labs. And if you get something wrong, I even let people make changes, although I don't want to have an enormous amount of regrading, because that becomes onerous for the TA. So everybody should be able to do well on the labs, but nonetheless, there's a lot of people who often don't hand them all in because they get behind. Don't get behind on the labs. I'm not going to be like the police, so I'm not going to come looking for you. It's your responsibility to keep up. Okay? And I'll go over a schedule in a little bit. In fact, I'll change. Let me just go over this now. So all this is on the website. Oh, I forgot to say, it's on these days. It's not a big surprise that everything is on the website. So basically, the link you use to get all the information is right here. Right? It's just my website. So you can actually Google my name, and my website comes up, or you can Google my name and this is actually incorrect, because it's ECE 637. It's 637. I changed that. So it's actually ECE 637. I have to correct that. Okay, so all this information is there. In fact, maybe I can even see if I can get this computer. Let me try to log in. Control, Alternate, Delete. Okay, sometimes you take a while to log in, so, it's going pretty fast. Okay, okay, it's doing something here. Okay, so anyway, this syllabus here, I updated it, and it shows all the lectures. We won't necessarily be exactly on target for this syllabus, but hopefully we'll be close. Sometimes we slip behind a little bit. But what won't change is the exam dates. So check those, put those dates on your calendars now. There's 2 midterm exams, and there are no makeup exams in this class. If you can't make an exam, you can come and talk to me, and there's options, but there's no makeups, okay? Because I can't. Every exam is a custom-made event, and it can't be reproduced. It only exists at one point in time and space. So you can see the basic topics we cover. I'm going to talk about that in a little bit more detail. So the other thing that's very important is hold on just a minute. It is the due dates for the lab. So the first lab is due at the end of next week. Hold on. And ECE 637. Oh yeah, see, it worked. It brought it right up. Can we go to the computer? Oh, it didn't work at all. What did I do wrong? So here, I click that. Oh, there it is. I don't know why it didn't work. Okay, so here, this is the main web page. Oh, I should make that spring EC. That should be 2001. I'll fix that. So here's the course information. This is the thing that we're just going over. And here's the course syllabus that we're just covering. Let's see. So, okay, these are the due dates for the lab. So the first lab is due at the end of next week. Oh, no, I'm sorry. Not the end of next week. It's the end of the third week. So I'm not going to come and track you down. You need to get these labs done on time. Now, for the off-campus students, we'll set up a system where they can email them in. And I haven't, in fact, I think, how many people in here would be, okay, last time I taught this course, what we did is we just had all electronic submissions. So what I did is had the students email in PDFs with their final labs. Is there anybody who doesn't like that idea? Is there anybody who actually prefers to work on paper? Now, in the first lab, there's some things in there where you're supposed to print out images. So we could reinterpret that to mean to copy and paste the thing into a Word document, I guess. It might not mean exactly. I mean, I'll be a little bit flexible on that, okay? But maybe we'll just work through everybody submitting it electronically, which just means that if you have any equations or something, you have to format the equations, or you have to write them on a piece of paper and scan the document as a raster that you can include. But it has to be emailed in as a PDF. I'll only accept PDF. Okay, so probably what I'll do is set up maybe some kind of email address that you can email things to, because I haven't really figured out a good solution as far as like a Dropbox type of an affair. So in that case, then both the on-campus and the off-campus students should be on a level playing field as far as submission of laboratories. Now, the off-campus students are a little bit delayed in terms of their lectures, so maybe I can give them a little bit of flexibility on that. But it's very important you try to keep up with this for your own good. Because what happens is later in the semester, the labs get fairly complicated. The last lab takes 2 weeks because it's a fairly complex lab implementing a conventional JPEG encoder, which I think is JPEG is still very widely used. Maybe not so much theoretically state-of-the-art, but the concepts in it are very important still. And it's very useful to implement that. So, but it takes quite a bit of effort. So if you're at this point right here on April 18th and you're like 4 labs behind, you're in trouble. Okay. So don't get there. Okay. Well, I'll talk about that a little bit more in a few minutes. Don't let yourself get behind. So this is your schedule that you can follow. All right. Okay, so maybe we can get back to the course information. I'll make this a little bigger. Okay, let's see where we are here. Okay, academic honesty policy. Okay, now, there's really 2 functions for me to discuss the academic honesty policy. One is the very real function that it's important that you understand what is considered to be okay and what's not. And there's nothing, I mean, you know, for all the very honest people in the room, policies vary from class to class. So what is perfectly legitimate in one class may be not legitimate in another. So it's important you understand what those differences are. Okay, so that is information meant for everyone. Okay, the other part of it, I apologize to all the honest people in the room, because the other part of it is for the small number of people who have, for which that caused me to have this discussion, okay? And so I apologize to all the rest of the people in the room. Unfortunately, there have been times in the past, oddly enough, when there have been problems with academic honesty in this class. And for those people, I am basically unyielding, okay? Don't fall into that category because it's a very horrible thing, okay? Okay, but the real reason why that academic honesty is very important is that as a student, you come to a university to study material because you, for the love of the knowledge, I think this stuff is really exciting and interesting, and then it also enhances your ability to pursue a career and achieve the various goals that you want in life, okay? And I can tell you, after many years of practicing the research and scholarship and profession of engineering, that the grade you get in this class, while grades are very important, is certainly not, the grade you get in this class is certainly not the most important thing that's going to ever happen to you in your life, right? And in fact, your sort of professional conduct and ability to work with other people and and be a valuable member of a team and society and your community is far more important than your grade in this particular class. Okay? So when people hire you in the profession, those are your ability to work as with integrity as a member of a team is much, much, much more important to your success. So what I'm really telling you is that dishonesty does not pay. It's really doesn't lead to anything good. Okay, so right. I'm sorry I had to say that for all the honest people in the room. Okay. Now that said, sometimes there are some very somewhat legitimate reasons, or some very legitimate reasons why people can get confused and have problems with misconduct issues. Okay. One is that they simply don't understand what the policies are, and the other is sometimes human beings in life, you'll find that in order to behave ethically and do the right thing, often it requires a little bit of planning. You have to think ahead to make sure you don't make stupid decisions. Okay, so let's kind of go over that a little bit. Okay, so first of all, obviously, copying from your neighbor is during an examination is not allowed, right? Now. In addition, modifying your exam solution and bringing it back for a regrade would be another example of something that would earn you an F in this course. Okay. By the way, any of these sorts of things would earn you an F in this course, at the very least. Okay. Now where it gets into things that are a little more complicated is homeworks and laboratories. And we don't really have homeworks, but we do have laboratories. You're certainly allowed to work with other people on the laboratories. In fact, you're allowed to work closely with other people. And in fact, you can work closely with me, so I'll tell you the answer. Okay? So there's no problem with that. But in the end, you need to write up your laboratory yourself. So what would be academically dishonest would be to get the finished laboratory from somebody else, put your name on it, and submit the PDF. If I found that you had done that, if you had like a duplicate copy of a submitted PDF from either a current student or a previous student, that would earn you an F in this course, and it has earned people Fs in this course in previous semesters, unfortunately. Okay. Now, also, if you have possession of a person's laboratory material from a previous year, I don't expect that you would ever have possession of completed laboratories from a previous year. That is not allowed. Okay, so you can work closely with other people. You can figure out how to solve the problems together. All that's fine, but you can't actually hand in somebody else's lab. Okay. So I think that's not an unreasonable standard. Okay. Now, and fundamentally, representing anyone else's work as your own, that would be considered to be a violation of academic honesty. Now, so where sometimes people have run into problems is that they wait till the last minute and they're like 5 labs behind, and it's 4 o'clock in the morning, and they're exhausted and they're not thinking very clearly, and they do something that they shouldn't do. Okay? Now, if you were to find yourself in the situation where you had, like, you were in this very bad situation because maybe you hadn't thought clearly in advance and so forth, and you were way behind on the labs, and there was no way you could complete all 5 labs by the due date, which was, say, 6 a.m. the next morning, okay? And it's 4 in the morning, okay? So what would you do in a situation like that? You're a good student, I can tell, okay? You would contact me, right? And then we'd figure out how to get the problem resolved. But the answer is never to cheat. Don't ever do that. Because for so many reasons. Not just because it's going to have a high probability of ending very badly for you, but also because it just it's not helpful, okay? So, sometimes students do things and they get themselves into bad situations. But come and talk to me and we'll figure something out, okay? It's obviously not a good thing, but don't plan on doing that and say, well, it's okay, I don't have to hand in any of the labs because I'll go and talk to Professor Bouman at the end. But, if you ever get in a bad situation, come and talk to me, okay? Okay, this is some crazy thing that the university tells us that we have to put into there, and I don't really understand what it means. But basically, it's some kind of legal thing. Okay, but basically, obviously, if there's any problem with the course, check the web page. I'll put a posting or I'll send an email. Okay. Now for off-campus students, there's special situations. Please read this thing carefully. Basically, what it says is that the off-campus students take the exams after the on-campus students have taken it. So it's their responsibility to make sure that they're not privy to any information that might unfairly give them an advantage. So they should avoid any contact with on-campus students during that period. If by chance, through no fault of their own, or through no intention on their own, they accidentally ran across the solutions to the exam or something like that, they should contact me. If you're ever in a situation, and this goes for any students, on campus or off campus, where there's a concern that you might have about violating academic misconduct policies, come and ask me. If you're not sure if something is okay to do, come and ask me. I won't hold it against you. If you ask me something and I say, no, you're not allowed to do that, that's okay. I won't think ill of you, okay? Just ask me and I'll tell you. Okay. So right. So I think that's pretty clear cut. Okay. Now this is just an outline of what we cover, and it shows which topics are covered by lab material. I think for this I can also go to the web page. Okay. So there's course notes here, and the notes have PDFs behind them. I might do some reformatting of this material now that we have the widescreen format. Okay, the laboratories. So these are the laboratories. You click on the laboratory, and there's usually a procedure. The procedure contains not just, it doesn't just tell you what you need to do, but it usually gives you some background information. Some of the in fact, the first lab requires that you do some ANSI C programming. So we use C. I mean, if you want to use C++, you can, but I want people to use ANSI C or ANSI C++. There is ANSI C++ now, I think, right? So the advantage is that ANSI C is very portable. So you only do, so if you write C, which is strict ANSI C, then you can move it between different platforms, and it's pretty bulletproof, especially now that most platforms use pretty standardized IEEE formats for floats and things. Okay, so the labs have a lot of introductory material which you can read, which explains how the theory behind the lab, as well as telling you what you have to do. And then there's data here you can download. So I think it's and okay, there's a package here, and now from time to time I have to update this, and I think this should be updated, but this is like stripped down C code that will read and write TIFF images and do some basic operations like that could otherwise be difficult. So it gives you an example program. You can compile and run that. If you have trouble compiling and running that, then come to me because there's something wrong and I need to update it. Or the problem is I have some of the same code that's in multiple locations, and sometimes I don't get it updated in all the places. Okay, so these are the laboratories. And this is important here. So this is the thing I told you about. Hold on, let me back up. This will make more sense if I do it in a different order. So this is a very important link here. Okay. This is a link to a web page, which is it's like a blog kind of a structure where you can communicate with other students about how to solve problems. So it's for your own use. But here I have some video lectures from a previous offering of the class, and hopefully they actually work. Let's see if they work. And in fact, everybody in this class should be able to actually access the videos that are being recorded right now. So this is kind of a video inside of a video. This is going to be kind of interesting. I have to do this just so I can say it's been done. Okay, so here it is. Let's see if we can fast forward. There I am. Yeah.
Thrown in the deep water.
I'm boring. Okay, hold on. Go away. Close tabs. Okay. Oh, no, I did the wrong thing. Okay. See, I was too aggressive in getting rid of myself. Hold on.
Digital source.
I got to figure out how to bookmark myself. Wow, that thing's fast. It must have... These programs just keep getting smarter and smarter. How did it know that? Okay. Okay, so these are video lectures, but you should be able to access these videos directly, and I'm going to email out a password. But you have to be on campus, or presumably, I assume if you run a VPN connection, you can probably be off campus. Okay, but this is very important. Previous offerings of the class. So if you go to this, I archive all the old offerings of this class. So if you go to a previous offering, you can go look at the exams. So here are here's the exam, and exam 1, and here's the solution to exam 1, I think. Yep, there you go. And the solutions may actually be correct. So then you can use them to check to see if you did the problems right. So, so that's where the study guide comes in. The study guide is like the homeworks. And what I've done is I've indexed the problems. So here you can see that in the spring 2009 final problem 1, it covered some problems related to this material. You don't necessarily have to do all these problems because they go all the way back pretty far, but it's a good idea to do. You should probably at least look at them and maybe work through all of them. It's really not a bad idea. And it gives you a convenient way to study for the course. My philosophy is if you can do every problem that I can come up with, you must know the material, or at least know it as well as I do. So these exams are from last year, so they're not correct. They'll get updated at the time we actually take the exams. Let's see. Okay. So I've covered the study guide and the course information and the exams. And so now we go to the course notes. I'm just trying to think. Are there any questions at this point? So here on this web page, I have all the notes for the class. You can see the topics we cover. So we start off with standard topics involving linear time invariant or space invariant systems, like the continuous time Fourier transform and the continuous space Fourier transform. And then we do the continuous space cases first. I think that they tend to be more intuitive for a lot of people. Maybe me. It's maybe because I'm an old guy and I'm used to thinking in differential equations or whatever. But then this material gets a little bit dry. So then we go to some applications of this. So the nice applications of this are in tomography and MRI, because for this material we don't yet really get into discretization of the signals. So therefore we can use the continuous space and continuous time Fourier transforms directly. And we can see how they can be applied to solving very important application problems in medical imaging. So I think that's kind of nice. And even for people who work in MRI, I think this is useful because you can kind of see some of the basic thinking of MRI couched in the language of signal processing. So it makes it a little bit, I think it's fun anyway. And we also do a little bit of imaging system stuff, like photography and so forth. Then, this is just a little sidebar we take, and in fact, it may not even be exactly correct. Well, there's two components. One is I talk about like C programming style, so my own personal philosophy on what to do in order to avoid writing really, really bad C code. Okay, so I have some simple, very, very stringent rules that I suggest you use that will keep you from doing really bad things. Now, I don't know if the programming skills of students have in general improved or gotten worse or stayed the same, but I don't know. But I still think these are valuable. Now, this tells you how to get ANSI C compilation on Windows if you're using Microsoft Visual Studio. But you know how Microsoft products are. They change all the time, okay? So I really, there's an asterisk on this. You have to figure it out yourself, basically, okay? And if you do figure it out, you can let me know, and I'll post the updated, correct things. But you have to set some flags. But every major C compiler will support compilation of ANSI C, okay? So it's just a matter of figuring out how to do it. Then we get into some discrete parameter systems. So instead of the continuous time Fourier transform, we have the discrete time Fourier transform, sampling and scanning, which are important in 2D, 2D filters. And the last time I taught the course, I did a little thing in eigensignal analysis, because it is a very useful technique that comes up a lot in imaging applications. So then we talk about image topology and segmentation, so some connected components analysis, some very simple algorithms. It introduces you to that, and students over the years have used this. I see that people, when they do their PhD theses, they often come in and they're using these connected components algorithms, so it's kind of handy stuff to have coded up. And edge detectors and some segmentation. And then we get into a big chunk of the class, which is on image perception, representation, and color. So this is a piece of the class that people sometimes feel a little bit uncomfortable with if you're a traditional engineer, because you'd say, well, I got into engineering because I didn't want to have anything to do with humans, right? Well, first of all, it's important to interact with humans in engineering, but that's a separate matter. But in fact, it's even worse than that. We're going to study humans, okay, in this class, which is a really scary thing. So humans are kind of messy because they don't, it's hard to write a differential equation down that describes them precisely. But nonetheless, we're going to take an engineering approach to modeling humans. So we're going to try to understand human color perception. And the reason is that images are almost by definition things that humans will look at. I mean, not always. It depends on your interpretation. But usually that's the interpretation of a picture, as opposed to 2D or multidimensional signal processing, which might be a signal that maybe you're not going to look at. But most images are assumed to be things that you're going to look at. So if people are going to be looking at them, then they're part of the system, the engineering system, and we have no choice as engineers but to accept that and to try to understand that component of the system and to model it. So we'll start off by trying to understand achromatic image perception and the basic concepts of contrast. And we'll start off by, I'll present some illusions that are very strong, which will break your underlying assumptions of truth. Okay? So, and then we'll get into color, the perception of color, and both from a kind of what you might say pedagogical or theoretical maybe perspective, and also from a practical perspective of implementation, and a little bit of color fidelity metrics. So we spend a lot of time on human vision. And then we'll talk about interpolation, decimation, and then we'll do some work in image enhancement and filtering. And for this, we actually have a lab where we do, and we also introduce concepts of training, which are very important in a lot of imaging and image processing applications. Training from real data, which is really a form of estimation, which comes back to probability. Then we do some digital half-toning, and finally we finish up with some stuff on source coding of images, which is basically like image compression, either lossy or lossless. So, and that wraps up with the lab on image compression. So I guess, so are there any questions at this point? If not, I think I can actually launch into some of the introductory material. Okay. So this is all, okay, I think I've been through all this. Basically, I covered it. Let me see, these are the labs. Oh, what is image processing? This is it. So image processing, in my view, is more than 2D signal processing or multidimensional signal processing. And the reason is that, image processing really implies that you're not just processing any form of two-dimensional data. You're processing some form of data which is related to the formation or acquisition of an image. So the analogy would be that image processing is to multidimensional signal processing as speech processing, say, or audio and speech processing is to signal processing. It's a particular form of data, and it's very important to understand the physical aspects of the modeling of that data. So in order to understand that, you need to understand something about the physics of the image acquisition system. And I talked a little bit about the modeling of human beings. So there's two types of modeling that we typically do in this class. One is sort of modeling that's related to physics, and it usually draws on basic physical laws, okay, like Newton's laws or the propagation of light in free space. And those laws are those quote-unquote laws, which are, of course, always subject to change, but in very, very minor ways usually, but are very well understood. And the problem is not in the underlying understanding of the physical behavior, that we have models that are, plenty accurate for anything we would want to do. But the problem is in figuring out how to simplify those models sufficiently and take the essence of them and apply them to our problems. Then we have the mathematics of the imaging, but then the psychophysics of the visual system. That's very different than the physical modeling of the imaging system, because there we don't really have precise models for humans. So those are based more on very high level models and usually stochastic kind of structures or some approximation. Okay, these are just some things that, this is old stuff. The image processing applications, I don't think I have to convince you very much that imaging is hugely impactful economically and socially and culturally. There was a time when I had to convince students that was important, that digital imaging was important, but I think that time has passed. Okay, so now, the continuous time Fourier transform, I think people should be familiar with this already, and if you're not, you need to do some remedial background. I'm not going to spend much time on it. This is the continuous time Fourier transform. Here are the units that we use to define it. There's some functions which we will be using throughout the class. The rect function, which is a square pulse. The step function. The sine function and the step function differ because the sine function takes on values of -1 and 1, and the step function takes on values of 0 and 1. The sinc function, which is the ratio of the sine pi t to pi t, and this function here is maybe specific to this class, which is the lambda function. I use the letter uppercase lambda because it looks like a triangle, and that's what the function is. Okay, so the lambda is what you get if you convolve the rect with itself. And then using, this we might want to spend a little more time on next lecture, but the delta function is something we'll use a lot in class. The delta function actually isn't a function, but it can be thought of as an operator, and it's used to find the impulse response of a linear time invariant system. So you're going to want to go over this material for the next lecture and make sure you're familiar with the continuous time Fourier transform, because I'm going to go through this very quickly. Okay? And maybe we can come back to me so I could say goodbye. So it was nice having you here. I'll see you next lecture. Thanks. Bye.